Hello, Skyhawks, and welcome back to another episode of SIP Zoyus, your semi-daily dose of math curriculum. Our topic for today is going to be graphing cubic and cube root functions. So cube and cube root graphs are created by plotting all the inputs, x's, and outputs, y's, for a cubic function and a cube root function. So we can see that these are our two functions right here, and these shouldn't be unfamiliar, right? We should know these, and we should know that what essentially each one is doing. This one is taking a number, it's multiplying it by itself 3 times. This is taking a number and it's looking for 3 multiples of the same number that are contained within that number, right? So we plugged in 8 here, right? If we went over to 8, we would see that we get out 2. And that's how these graphs are working. It's the input on the x and the output on the y. Likewise over here, if we plugged in a 2, right, so 2 for x, that would be 2 to the power of 3. That would then be 8, because 2 to the power of 3 is 8. Note these functions are inverses, so the cubic and the cube root are inverses, and we can see how they have this kind of symmetry over here, right? They kind of have this beautiful kind of tangled pattern that's going on, and it's coming about from flipping it over the y-x axis, right? Just further proof that these two are inverses. As well, if you want to convince yourself even further, pick a number, take the cube of it, right, so let's maybe pick 2. We take the cube of 2, that's going to give us 8, and then take 8 and run it back through our cube root function, so the cube root of 8 would equal 2, and thus bringing us back to the number we started with 2, right? It takes us from an input to an output, and then from that output back to an input. Cool, so these are our graphs right here. And notice the points which are around the vertex. The vertex is always going to be centered at the origin, so long as there's no shift in it. And then around there, our points are going to go over for our cubic function, over 1, up 1, over 2, up 8, and backwards, back 1, down 1, and back 2, down 8. And similarly, our cube root function is going to be the inverse of this, so we have our vertex still centered at the origin, but then our surrounding points are going to be up 1 over 1 and then up 2 over 8, right? The inverse of what we did over here. And then down, and then over 1, down 1, and over 8, down 2. Okay? So that's what our functions are going to look like. And here's some general format for our functions. So we can look over here, we see this is our cubic format, and notice it's incredibly similar to the square functions and the square root functions we've been plotting, right? We have h and k, which are going to be our vertex. Our multiplier is going to be a times b to the power of 3, and the reason why is because this b is caught up under the power of 3, right? We need to apply a power of 3 to this b before we can look at it as a straight multiplier, right? The multiplier isn't just b, it's b to the power of 3. And likewise, so that means our entire multiplier is going to be this whole thing in front, right? B with that third power and a with no power. So whenever these guys are larger than 1, it's going to be a vertical stretch. Whenever the absolute value of them is larger than 1. Whenever the absolute value of these is less than 1, that will be a vertical compression, right? And whenever we multiply, this makes sense because whenever we multiply things by 1, sorry, I can't talk. Whenever we multiply things by 1, they get bigger. Whenever we multiply things by, what am I saying? When we multiply things by values that are larger than 1, they get bigger. When we multiply things by values that are smaller than 1, they get smaller. There we go, finally got it right. Okay, and so now let's go ahead and look at our reflection. So remember, and this is the same with our square function and our square root function, a is going to be controlling whether it's vertically or vertically reflected. So if a is positive, there's no vertical reflection, it's just typical. We're not doing anything to it vertically. But if a is negative or less than 0, that means that we're going to have a vertical reflection, so it'll flip downwards. And likewise, very similar to with b, except b is on the inside of our operation, so it's going to be affecting our function horizontally. If b is positive, then there's no horizontal reflection. but if b is negative, then there's a horizontal reflection. And we can see how these rules are almost identical for our cube root function. They're just going to be with the cube root, of course. And I included this function down here because it's kind of just another way to think of the cube root and a great way to kind of relate it back to the cube function, right? Notice they're identical except for the power, and it's only this power which is going to change the shape of them. Alright, well, enough talking about it. Let's go ahead and do it. So we are looking to graph these guys and state the domain and the range. So our steps for doing this, we first want to graph the vertex, and then we want to start graphing surrounding points. So we want to go in here, we want to first find the vertex. So we're given a function. This is going to be a cubic function, we can tell because it has a power of 3. So our cubic function, remember, our vertex is just going to be h, which is right there, and k, which is right there. Now don't forget, h is a negative h, so we need the opposite of what's right there. So that means that h will be equal to -1, and k will be equal to -2. Right? We don't see a negative on our k, but we see it on our h. That's why we want the opposite for h, but the same for k. So that's our vertex, -1, comma, -2. We're going to go ahead and plot that. So back 1 and down 2. That is our vertex right there. And now let's go ahead and start finding our surrounding points. And the easiest way to do this, so you can go ahead if you like and plug in the values around your vertex. So you can plug in -2 to your function up here and see what you get out and then plot that. And you can plug in 0 to your function up here, see what you get out and then plot that as well. But the quicker way to do it is by understanding that the surrounding points are just going to always be systematically placed around the vertex, and just applying the multiplier and any necessary flips to them, and then plotting your surrounding points appropriately. Easier done than said, which is kind of a relief. So let's go ahead and look at how this normally looks. So it's a cubic function, so normally we go over 1, up 1, and back 1, down 1. But let's check out our multipliers. All right, so what are our multipliers? Well, we have a multiplier which is going to be 1/4 and -2, but don't forget -2 has a power of 3 to it. So really our multiplier here is going to be -2 to the power of 3, which will be -8 times 1/4, and 1/4 times 8, that's just like -8 divided by 4, which is going to be -2. Okay, so that's our multiplier. Now let's go ahead and use this to plot the surrounding points. So this means our absolute value of this is going to be 2. So that means we will have a stretch of 2 for this function. So instead of going over 1, up 1, we want to go over 1, up 2. Right? And instead of going back 1, down 1, we want to go back 1, down 2. We multiply the y value by our multiplier. Okay? Now, as far as reflections go, you want to pay attention to where the negative is placed. Is it placed on our b value on the inside, or is it placed on our a value on the outside? We see that it's placed on the inside on our b value, so that means it's going to be reflecting horizontally, not vertically. Okay, so let's go ahead and reflect this horizontally. So things that normally go over 1, up 1 are now going to go left 1, up 1. But remember, so typically we would have our point right there, and I'll make a little dot right there. But remember, we have a multiplier of 2, so instead of going over 1, up 1, we go over 1, up 2. Which brings us to right there. Okay, and likewise, normally we go back 1, down 1, but remember it's horizontally flipped, so we're going to go forward 1, down 1, and then a multiplier of 2, so forward 1, down 2. Not just down 1, down 2. Okay, and these are our first 2 surrounding points. Let's go ahead and see if we can plot some other ones. So then next on this graph, our points are going to be over 2, up 8. And so you got to think about that, right? So normally you go over 2, up 8, but we have a times 2 multiplier, so instead of going over 2, up 8, we're going to go over 2, up 16. We don't have enough room to graph that on here, but we can maybe, just kind of like mark it somewhere up here. I don't know. Actually, we shouldn't do that. It's an exact. We want to be exact in math. But this is about what our function would look like. We have 3 points. That looks good. We can draw our function just like that. Right? And that's what it looks like, right? And our domain, well, I know it looks like it's just going up and down, but the thing is, it is still going to continue to go left and right, right? And there's no x values that we cannot plug into here. So our domain is going to be negative infinity to infinity, right? Another great way to think about this is if you tried to put a picture frame around this, where would you put your picture frame? And the thing is, you definitely can't put your picture frame around the top and bottom, and you actually can't even put it to the left and right because it's still going to keep going left and right. So that's our domain. Now for our range, kind of like we said, it's pretty easy to tell that, you know, this guy's going to keep on going up and down, so it's going to be negative infinity to infinity, just like that. Boom. Cool. Let's go ahead and look at another one. Okay, so we want to go through both steps again. We are graphing a cube root function this time, and so our vertex, remember, now it's really tempting to do this. It's really tempting to go ahead and say that h equals -8, right? The opposite of that 8. But that would be incorrect. Pause the video and see if you can figure out why. The reason for this is because this 8 on the x is not multiplying both x and h. Right? This 8 is only multiplying our x. We look up here, we see the -2 is multiplying both x and h, which is +1. Here, that 8 is just multiplying x, and so it doesn't fit our format, so we can't just easily say, oh, well then h is 8, or h is -8. You can't say that. It doesn't fit our format. So step number 1, get that stuff out of here. We want to fit this into format. So y equals -1/2 cube root. And so here's where I want to get it to fit into format. So I see that b is multiplying both x and some kind of constant over here. So I want to pull out the multiplier that is on the x. So we're going to pull out a factor of 8 from both of these. That's going to leave us with x plus 1 inside of there. Just like that. And then, oof, running out of room. And then -3. Sorry, that's the -3 that's right there. Okay, so that's really what our function looks like. And now that we have that, it's easy to go ahead and say what h equals. H is going to equal -1. K is going to equal -3. So our vertex is then going to be -1, -3. So back 1, down 3, that is our vertex, right? Step number 1, you always want to plot the vertex. Step number 2, plot surrounding points. Again, so we can do this by either plugging in points which are around -1, right? We can plug in -2 and see where that gets us. We can plug in 0 and see where that gets us. But, you know, I guess the more conceptual way of doing this, and I think the quicker way, is just by using what you know the graph's already going to look like, and then applying your reflections and multipliers. Okay, so looking at this, our multiplier is going to be -1/2, and the cube root of 8. Okay, but now, right, that's not just multiplier of 1/2 and 8, that's a multiplier of 1/2 and cube root of 8. So we got to go ahead and calculate that cube root. Cube root of 8 is 2, because 2 can multiply 3 times to equal 8. So -1/2 times 2. And that's actually just going to equal -1. So we see we don't even have a multiplier. Oh, sorry. We don't even have a multiplier here. We don't have a stretch or a compression. All we're going to have is some kind of reflections. And we can tell because we have a negative going on the outside multiplier. So, right, so a is less than 0, it's a negative, so we're going to have a vertical reflection. So normally our function is going to be up 1 over 1 and up 2 over 8. Right, we can tell by what our function normally looks like. But instead, we're going to be reflecting it vertically. So instead of going up 1, we're going to go down 1 and then over 1. Likewise, down 2 instead of up 2 and then over 8. Okay, right, remember 8 from the origin, not 2 actual 8. this is -1, so 1, 2, 3, 4, 5, 6, 7, 8, right there. Alright, and let's go ahead and plot these other points. So the other points are going to be back 1, down 1, and back 8, down 2. So normally we go back 1 and then down 1, but instead, it's vertically flipped, so we want to go back 1, up 1, and then back 8, up 2. And then we will go ahead and make a beautiful graph, make a beautiful sketch of this. Right, and that actually doesn't look too bad. When you get these points on here, you really start to resemble the natural shape of it. So that's what our graph's going to look like. And our domain, well, we can tell it's just going to keep on going left and keep on going right, so that's -infinity to infinity. Or again, if you want to kind of take that picture frame analogy, could you put picture frames on the left and right of this? Well, no, you couldn't. So, they would keep on going to infinity, and likewise, can we put picture frames around the top and bottom? And again, I understand it can look like this stops going up, but it actually does keep going up and down, just very, very slowly. So we couldn't put picture frames on the top or bottom of this, so our range, our range would also be -infinity to infinity. Okay, goodbye.